So we have still 2 minutes.
Sure.
Yeah. He's a professor at the Department of Mathematical and Statistical Sciences at the American University of Sharjah, UAE. He holds a PhD in mathematics from the University of North Texas, USA. His research interests are in the area of commutative ring theory and graphs associated to rings. Dr. Badawi is the editor-in-chief of Palestine Journal of Mathematics, PJM. He has numerous publications, including book chapters, journal articles, and conference proceedings. I welcome you, sir. Please proceed with the talk.
Okay. Well, first, I would like to thank the organizer. Can you hear me?
Yes, sir. It is audible.
Okay. Thank you. I would like to thank the organizers for inviting me. And this is maybe my third talk in India within the last week. So maybe very soon I'm gonna apply for Indian citizenship. Uh, yeah, and I still have, I think, two more this month.
Okay.
So I thank you for inviting me. And my talk is 30 minutes or 40 minutes.
So it is, you can take 40 to 45 minutes and 2, 3 minutes for the question answer session.
Okay, I will not keep you that much. Anyway,
Okay.
this is a talk about total graph of a commutative ring without the zero element. Uh, you okay? Let me get to it. Let's see, because I am in full, I think this way. The arrows will work, I think, to go to the next page, or how I go to the next page using
So
full
just hero directions
direction.
keys.
Yeah, but that's what I'm
The
trying.
forward key.
Yeah, I'm trying that, but I don't know why it's not working. Oh, okay. Here is the introduction. Uh, as usual, my ring R is a commutative ring with the non-zero identity, and ZR is the set of the zero divisor. In 2008, David Anderson and myself, we introduced total graph of a commutative ring. And what is this about? We let R to be the set of all vertices. So all elements of the
Recording
ring.
in progress.
So all the all the elements of the ring vertices, and if you have two vertices x and y, then x and y will be adjacent, and adjacent, of course, you know what I mean connected by an edge. If and only if when you add them you get an element in the set of the zero divisor of the ring. Okay, because for me I think the introduction is more important, I mean, in my personal views, than what's next, because you need to know what I mean with this notation. So this is here, like I'm not sure if you can see it, what I mean with the total graph, and you need to know what I mean with the total graph. The vertices is the set of all elements of the ring. And if I have two vertices, then they are connected by an edge, if and only if when you add them, you come up with a zero divisor. Okay, then we come up with Z gamma R. As you see, this Z gamma R is induced subgraph of the total graph, where the vertices is the set of the zero divisor. Okay, and definitely by definition the set if you take this induced subgraph where you only take the vertices to be the set of zero divisor, then this graph will be connected. Why? Because if I have x is a zero divisor and y is a zero divisor, then I put 0 between them, then definitely x plus 0 is a zero divisor, and 0 plus y is a zero divisor. So this graph is always connected. So in this talk, what about if we consider z index by 0? And what do I mean with z index by 0? Here I'm going to consider the vertices to be all elements or all zero divisor of the ring except 0. So that's crucial here. You see, whenever you see z index by 0, I mean an induced subgraph, or just using street language, you think of it as a graph where the zero divisor of the ring except 0 are the set of vertices, and how you connect. When you add them, you come up with a zero divisor. Okay? And what do I mean with t index by 0? Well, again, t index by 0, it means I have the graph where the set of vertices are all element of the ring except 0. And remember how we connect. When we add two vertices, we should come up with a zero divisor. So in this talk, we're going to talk about z index by 0 and t index by 0. Again, z index by 0, the set of vertices is the set of all zero divisor except 0. So I'm removing the vertex 0. And t sub 0, the set of vertices, all element of the ring except 0. Okay? All right, and we still connect as usual. Two vertices are connected by an edge if and only if, when you add them, you come up with a zero divisor. Okay, here you see this result. What does it say? That if you have a non-reduced commutative ring, what do I mean non-reduced commutative ring? It means the set of nilpotent element is not 0. So non-reduced mean there are other nilpotent element than 0. Definitely 0 is an nilpotent element. But when we say non-reduced commutative ring, we mean there is at least one x in the ring where this x is not 0 and x to the n is equal to 0 for some n. And of course, you can read what will be the diameter of this graph. So the graph here, remember, z index by 0, I'm talking about a graph where the zero divisor of the ring except 0, the vertices, and how we connect. If we add two vertices, you get a zero divisor. And of course, all of you know what we mean with diameter. Diameter, like in a very basic graph theory, first you have to calculate the distance between two vertices. And how we calculate the distance between two vertices, like you go from A to B by walking on a minimum number of edges. I mean, this is really, I like this way to think of a distance. because you can go from A to B by using many, like edges. So we select the minimum number of edges that will get me from A to B. That will be the distance. And then the diameter, you take the maximum of all these distances. Okay, let's look at this theorem, and this is kind of maybe interesting because remember that from the introduction, uh, if I did not remove 0, then if I take the set of 0 divisors of the ring and I use the same definition, two vertices are connected if and only if when I add them I get 0. Sorry, when I add them I get a 0 divisor, then this graph is always connected. But when I remove 0, look at this result. If the ring is reduced and the minimum number of prime ideals is 2, exactly 2, then z index 0, this graph is not connected. So if I remove 0 from the set of 0 divisors, then the graph is not connected. And if you look at the next result, and again, what reduced? Maybe you're gonna tell me, what do I mean with reduced ring? Reduced mean 0 is the only nilpotent element. 0 is the only nilpotent element. So x to the n equals 0 for some integer n. That means x must be 0. That's what we mean with reduced. Okay? So it's naturally a question to ask, what about if the minimum number of prime ideals bigger than 2, like bigger or equal 3? Then z index by 0, this graph is connected. You see the theorem, if and only if. Z index by... Somebody talking? Oh, sorry. Then z index by 0, this graph is connected if and only if the number of the minimum prime ideal bigger or equal to 3. And if z index by 0 is connected, then the diameter will be either 1 or 2. What's that mean, diameter 1 or 2? It means I can go from A to B directly by one edge, or I can go from A to B by two edges, like A, C, B. I mean, this is what we mean with the diameter of z index by 0, either 1 or 2. Okay? All right, so where do we stand so far? If your ring is reduced and the number of the minimum prime ideal is 2, then this graph z index by 0 is always not connected. If the minimum prime ideal bigger or equal to 3, then z index by 0 is always connected. Okay. Okay, we still work with the reduced case. What about if the minimum number of a prime ideal is bigger or equal to 3 and less than infinity? Then if it's less than infinity, then the diameter is 2. Remember in the previous result, we said the diameter is either 1 or 2 if the minimum prime ideal bigger or equal to 3. And that mean could be infinity. But if you exclude infinity, then it has to be 2. Okay? All right, here is another nice, I mean, here is the thing. I mean, you give me like, okay, here is, I mean, a very good question. Like, okay, here is the graph, or you give me a ring, and here is the graph. So what? That's a good question. Well, in fact, being ring theorists, we are interested in studying like properties of rings when we know some properties of a graph, and vice versa. If I know some properties of the graph, then I should be able to get some information about the ring. Like this result here. If you read it carefully, if we have a commutative ring R, then the following are equivalent. If you tell me that Z index by 0 is not connected, then I know exactly the total quotient ring of R. The total quotient ring has to be von Neumann regular ring. And von Neumann regular ring, this is like, I will remind you with the definition, for every x in R, there is a y where x squared y equal x. I think most of you use von Neumann in somehow in your own research, or at least once in your career. This is a well-known in non-commutative ring. In fact, for commutative ring, also we use it, von Neumann regular ring. And let me remind you what I mean with the total quotient ring. The total quotient ring of R, it means localizing R, like you have the zero divisor. Let's go back. And then you take the set S, which is R minus the zero divisor of the ring. And then you construct R localized at S, you know, the ring of fraction. I think all of you know that anyway. Why did I mention this result? Because this is a clear connection between the ring structure and the graph. If you tell me the zero Z index by 0 is not connected, then I know exactly the total quotient ring is von Neumann with exactly two maximal ideal, and the total quotient ring is isomorphic to product of two field. Okay? Here is our, well, maybe this result is kind of nice. Why? Because in reality, a graph is finite. So here we study the Z index by 0 for finite commutative ring. If R is a finite commutative ring, then the diameter of Z index by 0 has to be either 0, 1, 2, or infinity. Okay? Look at number 2. The diameter is 0 of the graph, meaning what? The diameter of Z index by 0. If and only, meaning you only have one vertex. If and only if R is isomorphic to Z4, or that's clear. What about if the diameter of Z index by 0 is 1? If and only if R is a local ring with maximal ideal M, and the number of elements of the maximal ideal bigger or equal to 3. The diameter of Z index by 0 is 2, if and only if the number of the maximal ideal is bigger or equal to 3, or R is not reduced and the number of the maximal ideal is 2. And the last one, what about if the diameter? So here, sorry to stop here, to tell you what we are doing. We are characterize in a way all rings where the diameter is 0 or 1 or 2 or infinity. So we started like with 0, 1. Here is the result. What about 2? Here is the result. What about infinity? If and only if R is reduced and the number of maximal ideal is 2. So again, here is a connection between a ring structure and a graph properties. And this is, I think, the key for our study when we study a graph from rings. Okay, here between bracket, we split the question into two parts. The first one, if we consider Zn, so my ring is Zn, and n is not a prime, okay? Because if n is a prime, then definitely Z0 will be empty graph, okay? The diameter of Z index by 0 of this graph is either is 1 if P equal 2 and M bigger or equal 3, or the prime is 3 and M bigger or equal to 2. That's interesting in a way. Has to do with a connection, maybe number theory, with Y only prime 2 and prime 3. So this is a complete answer also to this question. What about the diameter of Z index by 0? And here I want to stop again and remind you what I mean with Z index by 0. It means the graph where the vertices is the set of all zero divisor of the ring except 0. And how you connect? When two vertices are connected by an edge, if and only if whenever I add them, I come up with a zero divisor. If your n is a product of 2 prime, then the diameter will be infinity. Okay? And the diameter will be 2 otherwise. So here is a complete answer for this kind of graph that you construct from Zn. What about the diameter if you have like N1, up to Nk? Then the diameter of Z index by 0 will be infinity for prime, this prime less than this prime. Otherwise, the diameter will be 2. Okay. All right. Remember that in the first 3, 4, 5 slide, the ring might reduced. What about for non-reduced ring? What about if your ring is not reduced? Here we study the girth. And let me remind you what I mean or what we mean with girth. Girth is the length of the shortest cycle in the graph. And what do I mean with length? Like, the number of edges we use to construct a graph. This is exactly what we mean with girth. Girth of a graph is the minimum number of edges we use to construct a graph. All right? And of course, if we don't have a cycle in the graph, then the girth will be infinity. So infinity mean we don't have cycle. Of course, if the graph is connected, then this will mean a tree, because definition of a tree is, connected graph with no cycles. Right? Okay. So here is a complete, like when is the girth is infinity. If and only if R has unique non-zero minimum prime ideal where this prime is the nil of R, which is the same as the set of the zero divisor of R. Okay? And that's kind of interesting again. Why? Look, a clear connection between some graph property and the structure of the ring. When you tell me the girth of this is infinity, I know what does the ring somehow look like. All right. What about for reduced ring? This girth, this result for non-reduced. What about if I study the girth if the ring is reduced? If the ring is reduced, then the girth will be infinity if and only if the set of minimum prime ideal consists of two. So the cardinality of the minimum prime ideal is 2. Okay? Otherwise, the girth will be 3. All right? So I read this. I keep saying that. I know maybe it's boring for some of you, but I mean, there is a point. I want to emphasize why we study graph from rings. Another clear connection between a graph properties and ring structure. Okay, let me skip this because I want to talk about, and here is the girth, in general for other type of rings. Yeah. What about if we move to the next ring, or next graph, which is the graph, the total graph without the zero element. You see T indexed by 0. This graph. And let me remind you, this graph, the vertices are all elements of the ring except 0. And how do we connect them? Two vertices are connected by an edge if and only if, when I add them, I come up with a zero divisor. All right? So here, this graph is connected if and only if this result, the total graph is connected. Look at number, I mean, this is funny. If the number of the elements of the ring less or equal 3, then this will be connected, T index by 0. But the other graph is not connected. What is the other graph? The other graph, which is the total graph, where I include 0 as a vertex. So the graph where 0 is a vertex is not connected. But the graph without 0 is connected. However, if the number of the elements bigger or equal to 4, then this graph is connected if and only if the total graph is connected. Okay, what about this result here? T index by 0 is connected if and only if either the ideal, the set of the zero divisors, if you form the ideal generated by this element, you come up with R, or R is isomorphic to Z2, or R isomorphic to Z3. Okay? And this graph is connected if and only if the diameter has to be less than infinity. Because this total graph, by the way, in the first paper, uh, okay, I don't know if I should talk about that or not. Because in many graphs, the diameter is always a number less or equal to 3 in many. This is the first graph I know where the diameter can be any number, the total graph. Like you give me a number, a million, I should be able to construct a ring where the total graph of the ring is that million. But this is not true if you study the classical zero divisor graph, where the diameter is always less or equal to 3. Okay, let me see what I can. Yeah, here T0, this is the total graph, also some more properties. I want to talk about something that maybe if there is a student here, they can, finish up that or work on it. Here is, I want to skip these and I want to introduce, uh, yeah, maybe I should talk about zero divisor path. Okay, remember, here is another way you want to look at it. I'll try to explain it using a very, I call it street language. What do I mean? Like you choose two elements, X and Y, from R star. What R star? That means X is not 0 and Y is not 0. Okay, then can I construct a path from X to Y where every other vertex is a zero divisor? Because look, in the total graph, you choose two vertices X and Y, and you go from X to Y, and there is no restriction. Like X could be a unit, and then the next one, like X1, could be a unit, and then X2 could be I don't know what, and then you go to Y. But here, I want to construct a path from X to Y where every other vertex is a zero divisor. Okay? This is kind of, for me, I don't know, it's kind of interesting. So here I'm adding more restriction on how I want to construct my path. I want to go from X to Y where every vertex, every other vertex is a zero divisor. Okay? So look at the result. There is a zero divisor path from X to Y if and only if one of the following hold. R has to be reduced. The minimum number of ideal has to be bigger or equal to 3. And R has to be generated by two elements. The ring R I should find two elements in the set of the zero divisor, and of course Z1 is not 0 and Z2 is not 0, and the ideal generated by these two elements should be R. If this is the case, then you should be able to go from X to Y by selecting zero divisor vertices. What about the case if R is not reduced and R is generated by Z1 and Z2? Okay? If R is not reduced, and this is the case, so here we have two cases. That's the first case. The second case, R is not reduced, R has to be generated by two elements, just like the first case. If there is a zero divisor path from X to Y for every X and Y, then R is not quasi-local. It's not quasi-local. And here, of course, diameter indexed by Z, what do you expect? You expect here I'm walking, I'm selecting my path from X to Y to be a zero divisor path. Okay? So here, when I calculate the distance between A and B using this new zero divisor path, I'm looking at all zero divisor path from X to Y, and I choose the smallest one. Okay, so this is a term that appeared in this paper, and I think you can do more on that by, like restrict your vertices, how to go from X to Y. Another way, here, here is it, to finish up my talk. Yeah. Another way is like you choose A and B, and you want to go from A to B, okay? How? By going through vertices that are not zero divisor. Remember, in the first case I gave you, I selected A and B. I mean, I want to go from A to B, and the path I'm gonna form consists of zero divisor. What about if I want to go from A to B, and every other vertex is not a zero divisor, which we call it regular path. This here, in particular, we don't know much about it. So if somebody like to study that, that will be interesting. And of course, this paper is already published, and it's on my personal webpage. You can go and you can get it for free. And I think this is good enough for me. I stop here. And I thank the organizer again for inviting me.
Sir, I can see some questions in the chat box. If you allow, I can read that.
Sure.
The first